Hello everyone, so now Group 18 from Section 3 will be presenting on the given task regarding the digital electronic assignment. So our group consists members of Deepak Kumar, anak lelaki Gobi Kumar, Ho Jin Shin, Shasmin Ariana binti Syafri Tauskan, and then Yap Sin Chin. Now I'll do a brief talk regarding the introduction here. So in digital electronics, there are three fundamental components such as finite state machine, which is FSM, and then there are counters and registers. So each plays a unique role in ensuring smooth operation. As in here, a counter tracks event, and then an FSM, which is a finite state machine, it controls system behavior through defined states. And then a register stores binary data temporarily.
Hello, my name is Deepak Kumar, son of Gobi Kumar, and my matrix number is DAE21203. Today I am going to discuss task 1, which is finite state machine FSM simulation using Tinkercad. Well, our question is design a Moray machine using 3 JK flip-flop for a transition state diagram. Well, if you look at this is our state diagram. Let me start with the preset state. If the preset state is on 0, 0, 0, the next state will be 0, 1, 1, and the following will be 0, 0, 1, and the following will be 1, 1, 0. If the preset state is at 0, 1, 0, the next state will be 1, 1, 1. So if you look at the table given, you can clearly understand how the state diagram works. Let's see. The preset state of QC is at 0, QB is at 0, and QA is also at 0. And the next state of the QC will be 0, but the QB and QA will be 1. For the second row, the QC, QB is in 0, and the QA is 1. Following, the next state will be 1, 1, 0. This is a simple explanation of how this state diagram working. Well, now let's move on to the excitation table for task 1. Here I have 3 tables in a slide. The first one will be JK flip-flop table, the second one will be the state diagrams explanation table, and the third one will be excitation table. Well, if you look at the JK flip-flop table, in the output transition, if the preset state is 0 and the next state is 0, the flip-flop inputs J and K. For J, it will be showing 0 and the K will be under don't care condition. Well, if you look at the preset state for QC in the table below, it is in 0 and the next state of QC will be also 0. In this case, the J will be 0 and the K will be under don't care condition. If you look at the excitation table, the first row and the first 2 columns shows the answer, which is 0 and X. Okay, now let's see the third row of the JK flip-flop table. When the preset state is 1 and the next state is 0, the flip-flops input J and K will be, the J is under don't care condition and the K will be 1. So if you look at on the table below, where in the 5th row of the Q is 1 and the 5th row in the next state of QC is 0. Now the output will be X and 1. If you look at the excitation table, the 5th row and the first 2 columns will be showing X and 1. So this is how the excitation table works.
So next, I'll be explaining for the K map. First, we extract the data we got from the excitation table. Then we got every input of J and K from the 3 input, which is QA, QB, and QC. Lastly, from the K map, we could easily make the Boolean expression for each J and K input. So, for the JC input, Boolean expression will be QA XOR QB. KC input Boolean expression will be QA bar plus QB. JB input Boolean expression will be QA plus QB bar. QA plus QC bar. Next, KB input Boolean expression will be QA. Lastly, JA input Boolean expression will be QC bar, and KA input Boolean expression will be QB bar plus C. So next, this will be our circuit and connection for test 1. We use XOR gate, OR gate, and 2 JK flip-flop. So the output will be shown in the next slide. So in here, the output will be just like the state diagram beside here. Will be from 0, 0, 0, continue on to 0, 1, 1, continue on to 0, 0, 1, and then continue endless lah. So you can watch the diagram.
Hello everyone, my name is Ho Jian Xian and my matric number is DAE2120318. Today I will explain a 4-bit trace register circuit using JK flip-flops and how it works based on a control table with different input conditions like clear, parallel loop, and clock pulse. On the left of my screen, you can see the logic circuit that we built for the simulation. On the right side, you can see the output table showing the result from the simulation. In this register, we control the J and K inputs to make the flip-flop behave like a shift register. The logic is designed so that each flip-flop takes its input from the Q output of the flip-flop before it. This way, the data shifts to the right with every clock pulse. Now let's begin the simulation together. I will change the input values and you draw how the output change step by step. So line number 1, clear is 1, A, B, C, all is 1. So we get the output is 1, 1, 1, 1. Line number 2, clear is 0, A, B, C, D input is 1, 1, 1, 1. So we get the output is 0, 0, 0, 0. Let's see number 3. Line number 3, clear is 1. Then the input B is 0. So we get the output is 0, 1, 0, 0. Let's see number 4. O is number 1. And swift clock pulse number 1. So number 1 is 0, 0, 1, 0. Then clock number 2, so get the output is 0, 0, 0, 1. Clock pulse number 3 is 1, 0, 0, 0. Close pulse number 4, we get the output is 0, 1, 0, 0. Clock pulse number 5, line number 8, 0, 0, 1, 0. Line number 9 is clear 0, then the all input is 1, so we get the output is 0, 0, 0, 0. Line number 10, clear is 1, then the input B is 0 and input C is 0. So we get the output data is 0, 1, 1, 0. Line number 11 is all input is on and clear 1. Clock pulse number 6, so we get the data is 0, 0, 1, 1. Then number 7 is 1, 0, 0, 1. Line number 12. Clock pulse number 7. 1, 0, 0, 1. Then clock pulse number 8. Line number 3 is 1, 1, 0, 0. Line number 14. Clock pulse 9 is 0, 1, 1, 0. Line number 15. Clock pulse number 10 is 0, 0, 1, 1. Thank you.